The effective mass of the spring plus the mass that I'd added.
Ah, okay.
5.793.
Is omega
Yeah, radians per second.
5.793,
Yeah.
all right, which makes our frequency
0.922.
and then our period.
One 1.085.
And what we had found experimentally, 1.092
That's pretty close.
versus our prediction of 1.085.
That's pretty close.
Yeah.
No.
Sometimes it comes close to an accurate prediction. This oscillation back and forth of some medium, if it can obey Hooke's law, then we can use a sine function or a cosine function to describe it. If it is, and if it can obey Hooke's law, if it can be modeled by a trig function without just a plain trig function with no additional term for dampening. It is in simple harmonic motion. Nicely abbreviated to SHM. So if I wanted to put the mass on there and then come up with an equation to describe it, generically, I get y, or whatever we're using to describe position, is equal to some amplitude times sine or cosine omega t plus phi. Let's assume time is equal to 0 at the point when I let go. We have up being positive. So first off, how would I find the amplitude? So what's the amplitude of this? Or what point am I establishing the amplitude? All right, well, let's do the other parts that we can do. Do we want to describe it by a sine function or a cosine function?
Sine.
Okay, why?
Because it starts from 0.
Did it?
No.
Sine starts at 1, doesn't it?
Starts at, no?
It starts at the extreme.
Oh.
So since I said, since we have up is positive, it starts at negative. So it depends on how you want to deal with the phase shift. If you don't want to deal with the phase shift at all, I'd recommend let's start with a cosine.
Okay. We'll do this.
Negative cosine. Omega we have over there somewhere. That's the 6.9839 radians per second times time. And then we're setting up so that phi is 0. But the amplitude, we still have a.
And just the distance from the initial starting point to one of the extremes.
Yeah, in essence, how far do I pull it down? So it's in some equilibrium position right there. I pull it down. How far I pull it down is the amplitude. So whatever that happens to be, I'll just say 5 centimeters. Now, if we had chosen to go with sine, my amplitude doesn't change, so it's negative 0.05 meters sine of 6.9839 radians per second time plus phi. And we need to establish a phi so that when time is 0, my position is negative 0.05 meters. In other words, when that is equal to 1. In other words, when that is equal to pi over 2. So 6.9839t plus 5 is equal to pi over 2. Actually, we're at time is equal to 0, so that drops out.
So pi is equal to pi over 2?
Yeah.
Okay.
That makes sense, that's why you use cosine.
Yeah. If you can possibly get phi to be 0, I've just done it somewhere. All right, questions? All right. So now, let's deal with pseudo simple harmonic motion. I have a mass on a string. I am going to assume an ideal, this is ideal, so this is massless. All of the mass is concentrated in a point mass down here. This is some mass M. So I have something on the string, I pull it back, I let go, it's going to swing. Force diagram. What are the forces acting on that mass?
Tension acting towards just the rope, up and to the right kind of.
Okay, towards the fulcrum. Pivot point, axis of rotation, whatever you want to call it. All right, so I got tension there.
Way acting down.
Anything else?
No.
All right. It is not in equilibrium. Which way is it going to accelerate?
To the right.
That way?
Yeah. And up.
And out.
Towards fulcrum.
Accelerate towards the fulcrum. Why is it going to accelerate towards the fulcrum?
Because.
Centripetal acceleration.
It wants to
Yeah,
restore
it's gonna go towards the center acceleration.
And we just lost him.
R.I.P.
He's like, "Hey, no."
I think that's the direction of the acceleration.
All right, so there's centripetal acceleration involved in that direction. So we do have this centripetal acceleration that way. What about the tangential acceleration? Is there any? Is the speed going to change? So if I pull it back and let go, it's just going to stay there?
No.
It would be this way, to the right.
That,
Well, yeah.
not that way.
Would it be
Oh, you're-
perpendicular to the force tension?
It would be, so it's, so we have tangential acceleration and centripetal acceleration both. Or we can do it in terms of, we have angular acceleration and centripetal acceleration if you want. But either way, I've got these perpendicular accelerations, and so we have set up here, there's our coordinate axes. I hat, J hat. So what do we need? So we did force diagram, did acceleration, coordinate axes, done, decomposition.
Break weight up.
Yep. And so, in terms of defining angles, typically for these, for pendulums, you define the angle with respect to the vertical. Seems to be some sort of tradition there. So I need to break weight up. I have weight that's acting straight down. In other words, parallel to the vertical, or vertical. I'm gonna break it up into, that angle there would be
Theta.
yeah, that's theta. Whatever I'm breaking up is the hypotenuse, and so I'm breaking it up like this. W sine theta, W cosine theta. So my force diagram is now magically turned into, I've got W cosine theta acting this way, tension acting opposite that, and then W sine theta acting perpendicular to those. All right, let's go to this one again. Equations of motion.
Well, just W sine theta equals, no. Well,
Zero.
mg, no. mv squared over r, no. I,
You've eliminated a lot of stuff.
okay.
And you correctly eliminated everything. Let's keep it simple. What's our template when we're doing equations of motion?
NA.
Yes. What's my other equation of motion?
That would be ft minus w cosine theta equals 0? No. Oh,
What you're
mv
calling Jacob
squared
a
over
liar.
r.
Pardon? What's that? Equals what?
V squared over
Mass times acceleration.
r.
Not the same acceleration though.
Huh?
Centripetal.
MAC. These accelerate one, it is centripetal, the other one's tangential. We can put a little T there if that helps differentiate them.
Math.
Now, the second equation here, we're not gonna do anything with. It's the first equation that's of importance. Substitution, we have a formula for W, so we've got mg sine theta is equal to m times my tangential acceleration.
Take out the M.
So we very nicely have g sine theta is equal to my tangential acceleration. Does this obey simple harmonic motion? Does it obey Hooke's law?
Yes.
How?
It oscillates.
It does, but does it oscillate properly?
It can be modeled by sine functions, so yes.
Well, recognize we have a rotational variable there, and we have a linear variable there, so we probably should get them in terms of either both rotational or both linear. I'm gonna recommend rotational. What we're trying to do is figure out and it's the same mistake I always make, so there's a mistake over there, we'll correct in just a second. We're trying to show that position is proportional to the negative of the acceleration. We're trying to get some sort of relationship like that. And revealing what the mistake is over here. Which way is it going to accelerate? Which way is the tangential acceleration? Okay, that way. Which way is theta?
Oh.
Zero is here, is down, and then we rotate it that way.
Oh, so it's like that way.
It's opposite the direction of the acceleration. From a physics point of view, the angle would be into the board, but There should be a negative thrown in here. W sine theta is opposite direction of acceleration. There's a negative on one side or the other. Then it got erased. All right. But we still, let's get in terms of a single system here. What's the relationship between tangential acceleration and angular acceleration?
Does it have to do with the slope?
No. Probably could come up with something there, but not what I'm going. What's the relationship between speed and angular speed?
Is that an
Okay, I'm looking for a math formula.
angle?
Say magnitude? I would say magnitude?
No, they would not be the same magnitude. They'd have different units, if nothing else.
One use pi.
Not necessarily, but it could use pi. I know we've been through this before. But what's the relationship between arc length and distance traveled for something rolling?
Am I talking about like normal arc length?
Yeah.
Okay, so arc length is like the S
Yeah, just
theta.
pi.
It's like R theta or something.
Yeah, S equals R theta. V is equal to
I've got R times D, derivative theta over D time.
okay, so if we take the derivative of this equation here, then we get V is equal to,
Oh, omega r.
yeah, R omega.
Oh,
So either way. And then A tangential is equal to,
What are we
Would it be
taking the
the
derivative?
integral of that?
what did you say?
Would it be the integral?
No, we're still doing derivatives.
Oh, so R.
What are we deriving with respect to
Time.
time?
R, it's not, is it alpha? It's the, yeah, that one.
We got these three relationships here between linear and rotational quantities. So my equation here now becomes G sine theta is equal to negative R alpha. The angular acceleration as this thing starts moving through this angle is alpha. It's the rate at which the rotation changes with speed. Or, yeah. And so we have G sine theta here. It's not quite still in this relationship of position is somehow proportional to the negative acceleration because I got my negative acceleration there, fine, but I got sine of theta. I don't have theta. So how do you resolve that? How do you resolve the fact that I don't have theta by itself?
Did you take the inverse?
No.
No. Okay.
Then I would have an arc sine on the other side, which still doesn't get us there.
Oh, man.
That's somebody has seen this before. All right, I guess I'm going to introduce you to the small angle approximation.
Small angle approximation?
Who in here is in Calc 3? Or, I don't know, maybe it's Calc 2, Taylor series, Maclaurin series?
We have not done that yet. We are in the series.
I don't remember those, those
Yeah.
are so hard.
Sine of theta, actually, any function can be expressed as the sum of polynomials or a sum of, yeah, let's think of polynomials. So sine of theta actually is theta minus theta cubed over 3 factorial plus theta to the fifth over 5
Okay.
factorial minus theta to the seventh over 7 factorial.
Puppy.
Did
I
you know, anybody?
Actually, I remember doing that.
Okay. Cosine of theta is just the derivative of that, so you get 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial.
Oh, it was just the derivative each time?
If I did the derivative, this is the derivative of that. If I did the derivative again, I'd get negative sign, because I'd have negative theta plus theta cubed over 3 factorial.
That makes it a lot easier, but for some reason when I did it, I just thought that I was adding one to the top and the bottom, and then oscillating the sign, but now I understand that it was just a derivative.
I trust you on that.
All right. And it's Taylor series or Maclaurin series, I always get those backwards. Now, obviously, if I stopped it. It goes on forever.
Yeah, that's not gonna happen.
Which doesn't really seem like it's gonna help, because suddenly I go from a single, a trig function here to a whole bunch of terms. But we're dealing with a small angle approximation. So if theta is small, so if theta is much less than 1, the two less than symbols mean much less than. I have no units here because I'm talking about radians. You want to write radians in for your own edification, go for it. So if angle is small, well, think about something small cubed, something small to the fifth, and so forth. These terms right here become insignificant. So if theta is small, then sine of theta and theta are pretty much the same thing.